Thank you for watching this video. In this video, we are going to introduce our design of a new endoscopic system. The system is a magnetic anchored endoscopy fabricated with soft materials. We expect this device to enhance the stage of minimally invasive surgery, facilitate the work of surgeons, and most importantly, benefit patients. Compared to traditional laparoscope, magnetic endoscope does not require long shaft and handle control, reducing interference with other surgical tools while visualizing the surgical sites at different angles. There are three major functions our system should achieve. The first is anchoring. The second function is local camera manipulation. The camera module should be lifted and rotated, visualizing different directions and increase the overall field of view. The third function is a system translation. Surgeons should be able to easily translate the whole system to a new position and observe a new surgical target that is previously obscured by other anatomical structure. Other than the above functions, we also try to fabricate this system with soft materials. This and increase the potential of the system to adapt to more complex contours, increase compatibility with anatomic tissues, and reduce the risk of trauma for patients. With the above in mind, we designed a system with one external magnet and two internal magnets embedded in a soft material construct. The soft material construct has three sections. First, the top section is a cylindrical cavity where a permanent magnet should be embedded and allowed to move within a horizontal layer. The lower section is a suction cup, which will secure another magnet and also the camera module. Between the two is the middle stem. Since the whole system is fabricated with soft material, the middle stem will not only link the top and the bottom together, but also allow bending by the two magnets' coupling force. Our system can be operated by moving the external magnet. Because of the coupling force between the magnets, the internal magnet also follows, and the middle stem will bend, lifting the camera to a certain angle. If the external magnet is further moved, then the internal magnet will reach the cavity wall, and this will drive the whole system to translate to a new position. Let's take a look at some demonstration we can provide. Here you can see the dexterity of this system is very high, and the camera can be lifted and rotated rapidly. You can also see our test for system translation. The system can be fastly translated to a new position with smooth motion and high camera stability. We also designed and fabricated an external magnet controller, which allows more refined camera manipulation. Here you can see the camera can be fixed at any given angles. To demonstrate the adapting power of our system, let's take a look at another test. Here we put the system on a curved surface and at an orientation against gravitational force. We see the system can perform target tracing, camera manipulation, and system translation independent of orientation, gravity influence, and the complexity of the working surface contour. To achieve all of the above was not an easy task. Let's take a look of the testing of some older prototypes to see how they perform differently. Here you can see a prototype with apparent high dexterity, but if you notice, the length of the middle stem limits this prototype to full actuation, which does not allow for fine camera control. In another testing, you can see the other prototype with a short middle stem, but because of the strong coupling force, the maximum bending angle of the camera is rather small, which limits the dexterity of the system. To address this problem, we used a magnetic simulation software to calculate the coupling force of different sizes of magnets at a range of distance, balancing this with bending moment of middle stem, material properties, and the weight of the camera. We offer you a new design of magnetic anchored endoscope that is fabricated with soft materials, intrinsically safe, miniature in size, reducing interference with surgical tools, and can observe surgical sites at multiple angles. With these, we wish to benefit both patient and surgeon, and visualize the future of minimally invasive surgery.